Okay, hello everyone. So today I'd like to present about my shielding calculation code. Basically, this code is developed for purpose of this project in the health physics class. This Excel spreadsheet has embedded the functions of the calculation of the calculation formula for the determine that the shielding thickness for various materials such as the lead, sheet, or the concrete. So this Excel spreadsheet has 7 tabs. It's kind of easy to follow. So first tab is showing that the introduction about how to use this Excel spreadsheet and what kind of input you need or what kind of calculation is going to be made through the each tab. And as you can see that the how-to tab and CTDI tab and the CTDI calculation tab and workload tab and CT room geometry tab and lead shielding and the concrete shielding for the result. So I can go over step by step, and then as you can see that the how-to page, as you can see that the first tab showing that the contents of this software, you can immediately change the tab by clicking this one of the link. So also there's a report or manual to how to use it. This CT room shielding or thickness determination or calculation Excel program, how to use it. So you can also use this documentation for as a manual. So basically the CT room shielding or thickness calculation Excel spreadsheet is basically using the CTDI 100 and the DLP method. So basically using the air karma and given the 1 meter away from the source. And basically we know that how to calculate the CT100 and the DLP we learn from the imaging diagnostic class. Secondly, you can determine that what type of the radiation. Obviously, CT has the photon source, and then we choose that the device. So I'm going to talk about that later. But the CT scanner, we choose a particular GE manufacturer, the healthcare manufacturer one. The model number is Lightspeed 16 Pro. The reason why we choose this one, this is one of the popular one, and also the just choose the randomly for the G unit. I can show you the CTDI numbers, and then we also consider that in on the market the lead shear thickness in commercially available as minimum thickness. So calculation provides a certain number, or but that number is supposed to be satisfied the commercial the product availability. Otherwise, you have to manipulate this sheet, mean that you have a more or much more expensive the material you have to consider. And even sometimes this kind of a requirement of the thickness of the material is not available in the market. So mean that you cannot really implement it into it. And secondly, it's kind of minor thing, but it's important. The ones you reported that the thickness in terms of the CIS unit, but normally we have to provide by the inch unit, in particular United States. That kind of unit should be easily adapted by the architecture or contractor. As I mentioned, that the most reference is most likely quoted from the Bushberger diagnostic imaging class textbook. And the last one is occupancy factor. We are using it here. So this is the note by the NCRP 49 report. So we follow that the occupancy factors by definition in this report. CTDI values actually they're provided by the manufacturers, and actually the 2000 through the 2004 IMPAC group actually the compiled whole kind of scanner depends upon the vendor and the different vendors and then the models and so on and so forth. So there's a whole bunch of things, and then we choose at the GE unit 16, light speed 16, and then we choose at the 120, the kV, the power, and we utilize this information, which is given by this line 42, for using the CTDI number for head and for body, for numbers or coefficient actually corresponding to the air or center or peripheral numbers. So this manual actually mentioned that the motivation of the contents and the goal to identify the radiation type, source, and location at CT room. And we actually pick up to the CT environment, and then we choose the particular device, which is the GE Healthcare, the Lightspeed 16 Pro, and the multi-slice the 64 to the 320. So talk about how to use it. So first of all, we have to calculate the CTDI calculation, and also using the workload, and then we calculated the transmission factors, which I'll talk about later, and then take into account the occupancy and the permissible dose and attenuations of the lead and the concrete calculation, and determine how much thickness of the shielding material is needed for this particular CT room or CT device. So I mentioned that CTDI calculation. Let me back up here. So here, CTDI calculation, we selected the GE Lightspeed 16 and the KP about 120 is value we choose. So this number is actually coming from the CTDI IMPAC group table. So we quoted this number. You can choose the different one if you want, but I choose this one. And for particular CTDI head, CTDI peripheral, CTDI air, and CTDI body air, CTDI body central, CTDI body peripheral. And scan length is approximately 27 centimeter. So that's kind of a general overall the scan length. And then easily calculated the CTDI whole body. Basically, the notation is given here, calculation about the column D and times 3 and 1 inverse, and column E, which is here, has a peripheral and the coefficient is 2/3. This is actually the standard notation calculation, how to calculate the standard, the CTDI W whole body and the CTDI W for head and CTDI W for body. So this kind of notation formula is already taken into account this ratio to ratio, and then CTDI volume is calculated based upon the CTDI W calculation divided by the E20. So E20 is going to be here. So it's kind of based upon the pitch number, and then this pitch number is corresponding to the particular the scanner type. So this is known. That actually the calculation that is actually determined the scale factors for each the protocol, and this scale factor should be taken into account later for the calculation of the CTDI volume. So then talk about the workload. So here is workload. So I choose the randomly workload like assuming that the 50 patients per week we have to treat it, and most of energy using it because you choose the 120 kVp, and different treatment site and contrast that we're using really depends, but I randomly use that head and neck cases, we have about 25% of the patient population, or pelvis is 55, and abdomen and body is about 15 to 5%. So most likely we have dealing with the pelvis as a CT scanner, like a prostate or other vaginal cancer scanner. So it's a percentage of the number of patients, actually the 13, the 20, 28, and 8 or 3 patients overall, that comes with the 50 patients per week. So, and then contrast, we're using it for the head and neck cases, we may use the contrast, or the abdomen and chest cases also we can use the contrast, like for the iodine, so to enhance the imaging. But other pelvis and the body cases, we actually not using the contrast. So the percentage of contrast and also the user input. So you can actually determine that which contrast they're using it, how much contrast they're using it per the site. So once you determine, this is user input. So once you determine that the patient scale factor 50 means that how many patients on this machine can taking care of per week. So you can change the number, and that number is going to be changing the air curmer calculations at the end here. So these numbers, basically you can change the basically number of patients. So it's here is 25% or 55%, the ratio between the site, treatment site or scanning site. Also, you can change the number of patients, like a scale, like 100 patient you may treat it last week, then it's changing the automatically the air curmer for the all for all patients for the head, and the air curmer for the all patients for the body. So right now I choose it 50 patients. Then this kind of workload you can take into account the basically all information already given by the IM here's IMPT impact the group and the machine dependent, device dependent, and then the workload is actually only to consider that how many patients you are treating, how many contrasts you're using it, and then automatically can this table can calculate the air curmer for head for all patients and the body air curmers for all patients. And next one is the CT room geometry, like a dimension. And basically a survey point you can define where you are interested in. So for example, SP1 is a survey point 1, SP2 is a survey point 2, and so on and so forth. In the center, isocenter of this CT is indicated by the star mark, and then this is a place, and then you can measure that the distance between the isocenter to the survey point 1 through 6. So we have SP1 through SP6 that is corresponding to the control room door and the CT room door, and the left side, the right side, and back side door, and control room door. And ceiling is actually the this is a top view. So basically the perpendicular height is actually given by the number here. So from the isocenter, that is distance. So basically the input is given by the fit, so automatically changing the meter. So if we have a different number, for example, here is 10, then the number is automatically changing. So whatever number you survey of your CT room, then you can change this number, this column, and automatically calculate the in meter unit. Then based upon the DLP method, so which is the method between the Kerma of the head and the kerma of the body, some of this unit from the previous workload case here. So some of them head and body. So they take into account, and then calculating the distance. And this one isocenter is by definition is 1 meter. So that's why I put in the 1 here. And the other one is kind of a R square rule. So you have to apply that. Then they can calculate the DLP number, which is a milligray unit. And then the transmission factors can be calculated based upon the given the DLP method, the dose in here. By the way, this is actually assumption about the occupancy factor is 1 all around. So you can change this occupancy factor based upon which rooms attached to the left side or right side or behind or door or something like that. So then the same things mentioning about the IM packed table and the CTDI 100 value and DLP method is already given by these numbers. So these numbers basically weekly averaged error kerma, so a WAAK at 1 meter definition. So this is actually following by the NCRP 147. And then the other one actually, this one actually, isodose map is provided by the manufacturer. So we can actually using this isodose map later and compare to the result based upon the DLP method. So we can talk about it later. So as I mentioned, the workload calculations is done by this page, which is here. So it's actually workload is as a user input, and you can select the random patient percentage based upon the site, and also based upon how much construct you use, and that's actually user input, and then automatically calculated the error kerma for whole patient body and head. Then based upon the WAAK and using the DLP method, and you can calculate the DLP, and then based upon the DLP, and you can calculate the transmission coefficient in each the barrier. So this barrier is corresponding directly connected to the calculation and estimation of the thickness of the shielding wall. So lead shielding walls. Next slide is talk about next slide actually which is the estimation of the lead shielding thickness for each survey point. And this thickness is calculated by the formula using the transmission factor B for lead, and then the other one case is the concrete. So occupancy factor is also the kind of user input, but for the moment I use all 1, but you can change it, but then automatically number going to be updated based upon what occupancy factor you're using. So then calculation for the lead shielding, as you can see that this is the same. These are actually the same table, which I showed the CT room table here. The same calculation from the transmission factors based upon the DLP method, the kerma, and then the lead for the lead shielding material, the requirement of thickness, basically using the formula which is published in the 1983 is Archer's this fitting parameters based upon the CT KB value, KBP value, and the alpha beta is given, and the gamma is also given. Then you can calculate the basically what kind of thickness is required based upon the alpha beta, gamma, and the B factor. So we know everything, so we can calculate this simply from this formula. So this is actually what the lead thickness is required for each survey point. So pretty much about less than 2 millimeter each the survey point. So based upon the occupancy factor is 1. So you can, if you want to change the occupancy factors, number is going to change. For example, that this ceiling is, there's nothing is in there, then 0.2, then number is going to be changing, drop downs, how much less pad thickness is required. And same way, but different shielding material, which is concrete. So we use the same formula, but not exactly the same formula, but this time is actually the same formula but different at the coefficient for that, because we have different material. So this number is kind of from the also the same the publication. So we utilize the concrete. I think the concrete is just a normal concrete, about 150 pounds per cubic feet. Sorry. So then using these numbers, alpha, beta, and gamma, and the B transmission factors, and then you can calculate how much concrete shielding thickness you require for each survey point. So it's basically the same techniques we use in the lead shielding cases. So this is kind of how that the express sheet is working. So for the back to the manual, so then you can explain the same thing, lead shielding thickness for the DLP method, for the lead shielding thickness required, same number you can see here. It's the same as concrete. Concrete is also the same method we are using, but different coefficient for the concrete. So the number is kind of consistent with what we have in the Excel spreadsheet. So compared to these two different methods, two different material, and you can see that what kind of thickness, lead thickness, and concrete thickness is required in each survey point. At the same time, I mentioned that the isodose map technique also the popularly used, which is basically manufacturers provided by the isodose line around the CT machine, and then you can calculate the distance and then put into the same formula, and then you can calculate the thickness again. So as you see that the two different techniques for the lead and for the concrete, they're pretty much consistent within the 2 or 3% uncertainty level. So this is all about, and if you have any questions, then let me know. We can go over together later. Thank you.